Oh, namaste children. Just a moment, please. A hearty welcome to all my beloved students of 9th standard mathematics session, chapter number 5, triangles. This is the fourth and the last session for this chapter, children. I am T.K. Prasannamurthy, retired headmaster, Vijaya High School, Jayanagar, Bangalore. In the previous session, that is in the third session, we had discussed the following. Let us quickly recall them. The two fundamental theorems on isosceles triangle regarding the sides and the angles, that is theorem 5.2 and 5.3, along with the last two golden rules to determine a pair of congruent triangles, that is SSS and RHS. So these are all the things that we have discussed so far in the 3 sessions, children. Can you recall them? Yes. We hope that you have done the homeworks given to you, worked example from 4 to 8, exercise 5.2 and 5.3. Please show it to your teacher and try to get more information regarding them. Okay. Now, we have also understood one important theorem, that is, if two sides of a triangle are equal, then two angles facing them are equal. This is theorem 5.2. Okay. In the previous session, we have proved this theorem by using SAS rule only. Okay, let us try to recall it. So this is the figure, data to prove and construction. The construction is, we need to draw an angular bisector like this. So this is the proof. Just compare those two triangles. You will understand that they are congruent on account of SAS rule. Therefore, the corresponding parts are equal. Angle B and angle C are equal. We have proved this theorem 5.2 using SAS test only, children. Okay, this is the figure. Is it possible to prove using RHS or SSS or ASA? If so, what changes are to be made in our construction, children? Okay, let us try to prove theorem 5.2 using RHS rule. So this is the figure, data to prove, and if you want to use RHS, the construction that you have to make is, we have to draw AD like this, perpendicular to BC. Once it is perpendicular, you can easily prove that these two triangles are congruent on account of right angle hypotenuse and a side are equal to right angle hypotenuse and a corresponding side. Therefore, they became congruent on account of RHS. Once they became congruent, the corresponding parts are equal. Therefore, angle B and angle C are equal. So, we could prove using RHS rule also. Okay. So, we have proved the theorem 5.2 using SAS and RHS. Now, let us try to prove the same theorem 5.2 by using SSS. What is the construction, children? What construction you wanted to do it now? Come on, look at the figure. So, this is the figure, data to prove, and if you want to use SSS, the construction is, we have to choose the midpoint of BC, call it as D, join A and D. This is the median. So, you got two triangles, compare them, they are congruent on account of SSS. Once they became congruent, the corresponding parts are equal. Therefore, angle B and angle C are equal. Hence, it is proved. So, we could prove this theorem 5.2 using SAS, RHS and SSS. Is it possible to prove using ASA also, children? Look at the figure. No, it is not possible. It is because of this reason. In a triangle, we can draw a perpendicular from a vertex to its opposite side, or an angular bisector of an angle, but not the perpendicular, which is also the angular bisector from a vertex to its opposite side. Okay, so the proof for theorem 5.2 we could do in 3 ways. So if you want to, if you draw the angular bisector, you have to use SAS. If you draw the median, you have to use SSS. If you draw the perpendicular, then you have to use RHS. So in 3 different ways, 5.2 theorem can be proved so beautifully, children. Yes. So now let us go to the converse of this theorem, which we also already understood in the previous session. What is the converse? If two angles of a triangle are equal, then two sides facing them are equal, children. Correct. So, this is the figure, data to prove and construction. Can you recall this, children, which we have already explained in the previous session? Okay. Now, these two triangles became congruent. It is so obvious from the figure that two angles and a side are equal to two angles and a corresponding side. Therefore, by ASA, they became congruent. Once they became congruent, the corresponding parts of congruent triangles are equal. Therefore, AB and AC became equal. Okay, this also we have done in the previous session. Okay, instead of drawing AD perpendicular to BC like this, observe the figure carefully. So, instead of drawing AD perpendicular to BC, we can draw AD the angular bisector of angle BAC like this. Okay, so you can even draw the angular bisector. In both the construction, we use ASA only. If you draw a perpendicular, if you draw the angular bisector, you can observe the figure. We use ASA rule only in order to prove this. So, theorem 5.3 can be proved by ASA only by two different construction. One is draw the perpendicular or draw the angular bisector. See how ASA is used in a theorem and proved by two different construction. So wonderful, children. Note that the above theorem can be proved by using ASA only, by two different construction, but not by using SAS, SSS, RHS. So take this as an activity and please verify whether it is not possible to prove this by SAS, SSS or RHS also. Okay, so this is 5.2, this is 5.3. This can be proved by using SAS, SSS and RHS, whereas this one can be proved by using only ASA rule only, children. You got this point? Yes. Now, let us try to understand in an isosceles triangle like this, the perpendicular drawn from the vertex to the base. Okay, so observe the figure here. This is the perpendicular drawn from the vertex to the base. The median drawn from the vertex to the base. Observe the figure. This is the median drawn from the vertex to the base. And finally, the third one is the angular bisector of the vertex. This is the angular bisector of the vertex, or how they are interrelated. This we shall try to explore it now. Observe the figures carefully. Okay, now let us take up one by one. So, this is the first one, children, statement for this. So, in an isosceles triangle, the perpendicular drawn from the vertex to the base is, first point, median to the base, and secondly, it is an angular bisector of the vertex. Okay, so the figure is this. In data we write two sides are equal, or even you can write two angles are equal, and the second point is we have to draw AD like this, perpendicular to BC. So, given this, we have to show two things, children. Point number one, BD and DC are equal and angle BAD and angle CAD are equal. So, this perpendicular is going to bisect the base and bisect this angle also from which it is drawn. These two can be proved in one single stage, children, by just comparing these two triangles. See, these two are congruent because of ASA criterion. Two angles and a side are equal to two angles and a corresponding side. So, therefore, they are congruent. Once they became congruent, the corresponding parts are equal. Therefore, BD and DC are equal and these two angles are equal. Hence, it is proved. Okay, let us state it in another way. So, in an isosceles triangle, the median drawn from the vertex to the base is point number one, perpendicular to the base, and secondly, it is going to be the angular bisector of the vertex. We can call this as converse number one to the previous theorem. So, here is the data figure to prove everything here in this slide. So, in point number 2, we will write that BD and DC are equal. In the previous one, we wrote that AD is perpendicular to BC. So, given this, we have to show that point number 1, these two angles are equal, and secondly, this AD is perpendicular to BC, that is, these two angles are each of them equal to 90. All these things can be easily proved by just comparing these two triangles. These two are congruent on account of SAS. Look, children, SAS of this are respectively equal to SA and this side. Therefore, they became congruent. Once they became congruent, these two angles are equal. these two angles are equal. Do you know the reason? It's all because of the corresponding parts of congruent triangles. But how to show that this AD is perpendicular to BC? It's quite easy, children. You know that this plus this is 180 because they are adjacent angles of a linear pair. So the sum is 180. These two angles are equal. Don't you think it means that each of them is equal to 90 degree? Hence AD is perpendicular to BC. This is how we are going to prove. So finally we can put it like this. In an isosceles triangle, the angular bisector drawn from the vertex to the base is number 1 median to the base. Not only that, it is perpendicular to the base. This we can call it as converse number 2. So the proof is this, the same figure, data, the first point remains the same, only the change is in second point, that is these two angles are equal, that is AD is the bisector of angle A. Given this, we have to show that BD and DC are equal, and secondly AD is perpendicular to BC. Very easy, children. In the same way we can prove this. So again compare these two triangles. Don't you think two angles and a side are respectively equal to two angles and a corresponding side? Hence these two became congruent on account of ASA. When these two became congruent, you can simply think of the corresponding parts. These two sides are equal and these two angles are equal. Once again, this angle plus this angle is 180 because adjacent angles of a linear pair, they are equal and sum is 180, which means that each of them has to be 90. So let us sum up all the things that we have learned. So this is the first one regarding the perpendicular, then this is the converse to this is the figure, and finally so this is the converse to this. So all these things can be beautifully written in one single slide only. Okay? Yes. Here is a model, a teaching aid in order to understand the interrelationship between the perpendicular, the median, the angular bisector in an isosceles triangle. Each is the converse of the other and it forms a wonderful cycle. Please try to remember this in your mind permanently, children. It can be hooked to a stand or it can be removed and kept on a table like this. Now, congruency in triangle, children, has a very wide applications. Okay, the 4 tests on congruent triangles, that is SAS, ASA, SSS and RHS, are fundamental by which many concepts in plane geometry can be easily understood. To name a few, the first one is, for all the constructions we discussed from the middle school to high school can be given justification. Look at this figure. This we have already understood in the previous classes. Given the perimeter of a triangle and two base angles, this is how we are going to construct. This is all based on SAS and SAS criteria only. So with the help of the SAS criterion, this construction is taught to you. Second point, most of the theorems problems in geometry are based on congruency of triangles, and the proofs for similar triangles theorem are based on congruency of triangles, and the concept of 6 trigonometric ratios can be clearly explained with the help of similar triangles. Okay. Finally, children, the properties of chords and tangents can be easily proved using the test on congruency of triangles. So this is the advantage of learning congruent triangles. By this time, you would have got some idea as to how to write a theorem neatly and can be presented by just maintaining the symmetry. Here are a few tips for you, children. Always write the theorem at the top of the page, make 2 different paragraphs, one for data, another for theorem. Write the figure at the center of the page using sharp pencil, okay, protractor, scale, compasses, everything, and have a beautiful outline like this. And this is our margin. Draw vertical lines, very sharp vertical lines like this, and on this you can mark the semicolons one below the other exactly, so that you can write data to prove construction and prove exactly one below the other. Let it be in uppercase. Right and equals, parallel, perpendicular, greater than, less than, congruency. See that all of them come exactly one below the other. Say in date, if you have got two different points, make it as point number 1 and point number 2. In proof, you may be having 3 points. If you are using RHS, always write the right angle first and then the hypotenuse, then the side, children. If you are using SAS, first side S, then the included angle, then the side, and if you are using ASA, always write the angle first, then the corresponding side, then A. This is how you must write. And in proof, for every step we are going to give the reasons. So open the brackets exactly one below the other and close it also one below the other, and this is the symbol for because. So make it all of them align one exactly below the other. Okay, write QED at the bottom, right bottom. Construction, please do it in the dotted lines. Start writing the proof from the top of the page only. Once the proof is over, rub off all these vertical lines. So if you are writing theorem and converse, write it in one left page, and on the right page you always write the converse to this theorem. Okay, so these are some of the fundamental concepts of congruency of triangle, children. Let us celebrate this memorable moment in the studios with our director and our team meaningfully. This is how we shall show our gratitude to our great mathematicians. Children, so far we have understood the equalities in a triangle. Okay, so equalities we have understood. Now let us try to understand the inequalities in a triangle. Inequality means unequal. Okay, plural form of inequality is inequalities. Look at this triangle, children. Among these two sides, definitely this is longer than this. Therefore, what is the angle facing this? When compare this angle with this, definitely this is greater than this angle. Conversely, among these two angles, this is 60 degree, this is 45 degree. Therefore, this is bigger than this. Therefore, look at the side facing this angle and this angle. The side facing the greater angle is greater than the side facing the smaller angle. So these are the fundamental theorems on inequalities. So it is given in our textbook as article number 5.6. Now, so in a triangle, greater side has a greater angle opposite to it. This is given as theorem number 5.6. So this is the figure. So data is in triangle ABC we have, if you compare AB with AC, definitely AB is longer than, greater than AC only. Okay, given this, we have to show that the angle opposite to this is angle C, and angle C is definitely greater than the angle opposite to AC is B. We have to show that angle C is greater than angle B. So this is the proof which is not given in our textbook. That's why I just quickly run through the slide. Now what about the converse to this, children? This is 5.6. So this can be stated like this. In a triangle, greater angle has a greater side opposite to it. Correct? Okay. Now the figure and data to prove everything is, you are able to see in this slide. ABC is a triangle in which angle C, when compared with angle B, this is bigger, this is smaller. So we have to show that the side opposite to angle C is AB. AB is definitely greater than the side opposite to angle B is AC. So AB is greater than AC. And this is the proof by contradiction method. Again, this is not given in our textbook, hence I am quickly running through this. Okay, so just compare the theorem 5.6 and 5.7. Data has become to prove, and to prove has become data. Okay, So in triangle ABC, this angle ACB is an obtuse angle. So this is an obtuse angle triangle. So the angle ACB is greater than 90 degrees. So AB is the longest side. So the side facing angle ACB is AC. So in an obtuse angle triangle, the side opposite to the obtuse angle is always the longest side. So exercise 5 point number, problem number 1, let us try to understand this. Show that in a right triangle, hypotenuse is the longest side. Here is a right triangle in which angle ABC is equal to 90. We have to show that this hypotenuse AC is greater than AB and BC. The proof is very simple, children. Just in one single line only you can prove this. It's all because of 5.7. Now, if you observe these three angles, among these three angles, this angle is the greatest angle, being 90. Therefore, the side opposite to is AC. So, AC has to be the longer than AB and BC. Hence, it is proved. Okay. Now, let us try to understand one more very interesting property with regard to inequalities in a triangle. Here is a scalene triangle with each side 6, 8 and 9 centimeter. Have you ever bothered to see the sum of two sides of a triangle compared with the third side? Shall we do that here? So, you will see that sum of any two sides, if you take like this, it is always greater than the third side. You may be wondering, the sum of two sides may be equal to the third side or lesser than the third side. This we can try to understand by considering a construction like this. So here BC is 6, AB plus and AC are 4 and 2 centimeter. If you add these two, you get 6 centimeter. Here, if you add AB and AC, it is 5 centimeter, and definitely AB plus AC is lesser than BC. So first we draw the base BC like this, with B as center, with 4 centimeters as radius. We cut an arc like this, with C as center. Since AC is given as 2 centimeter, we cut an arc. See, they are not at all intersecting at all. They are just touching at a point A. Whereas here, with B as center, with 3 centimeter radius, we cut an arc like this. With C as center, with 2 centimeters as radius, we cut an arc. See, they are unable to intersect at all. They are not even touching also. So, it is impossible to construct a triangle when the sum of two sides is equal to the third side or it is lesser than the third side. Hence, sum of two sides of a triangle is always greater than the third side, children. This is given as theorem number 5.8 in our textbook. Shall we prove this, children? Okay, here is the proof. Okay. Now, data is ABC is a triangle, and we have to show that sum of AB plus AC is greater than BC only. Okay. So, what is the construction? This needs little construction. We have to extend this BA to D such that AD is equal to AC. Once you do that, join D and C. The proof is this. If you look at this triangle ACD, we have AD and AC are equal because of construction. Therefore, the angles facing them are equal because of theorem number 5.2. So, these two angles became equal. Now, look at this angle BCD, children. This angle BCD, can we write it as the sum of angle ACD plus angle ACB? Can we write like this? Definitely we can write. So, therefore, it is very obvious that angle BCD has to be greater than angle ACD because of axiom number 5, which states that the whole is always greater than the part. Instead of angle ACD, we can write angle ADC. So, we got in this triangle BCD, we have angle, this whole angle C is definitely greater than angle D. Therefore, we can conclude that BD, the side opposite to this greater angle is BD. BD is greater than BC because of theorem number 5.6. What about BD, children? Can we split BD as BA plus AD? BA plus AD is greater than BC. But AD, this AD and AC are equal. Therefore, in place of AD, we can write AC in order to get the required result. So, BA plus AC is greater than BC, which means that the sum of two sides of a triangle is greater than the third side. Hence, it is proved. I would like to discuss with you one alternate proof for this, a very simple construction. So, just draw AD perpendicular to BC like this, children. See, we got two right triangles. Let us take one by one. So in right triangle, this is the hypotenuse. Therefore, AB has to be greater than BD, because we know that in a right triangle, hypotenuse is the longest side. AC is longer than DC. Now, if you add these two inequalities, we get AB plus AC is greater than BD plus DC. What is BD plus DC, children? Look at the figure. BD plus DC is nothing but BC. Wonderful. We got the result in just hardly 3 steps. So hence it is proved. Okay, so now these are the two activities I am suggesting you. You also prove that BC plus AC is greater than AB. In this case, AB plus BC is greater than AC. They suggested the construction also. Please take up this as an activity and work out and show it to your teacher. So now let us go to the optional exercise question, that is the 5.5 exercise. For the first 3 problem, here are the hints, children. So here is a scalene triangle in which S is the circumcenter. Circumcenter means it is a point where all the 3 perpendicular bisectors of a triangle are concurrent, and this point, a circumcenter, is equidistant from all the 3 vertices. So SA is equal to SB is equal to SC. So here also a scalene triangle is there in which I is called the incenter. Incenter means it is a point where all the 3 angular bisectors of a triangle are concurrent, and this point is equidistant from all the 3 sides of a triangle. So use these hints and try to solve the first 3 problems. So let us go to the 4th problem and the last problem. So here is a regular hexagon and a star are given. We have to complete the regular hexagon and star shaped figures by rangolis and by filling them with as many equilateral triangles of side 1 centimeter as you can. Count the number of equilateral triangles in each case which has more equilateral triangles. This is the question. Children, you also know that in a regular hexagon, all the interior angles are equal. Each of them is equal to 120 degrees. Whereas in this star also, can you see one regular hexagon is there inside this? So therefore, here also all the interior angles are 120 degrees, and there are 6 equilateral triangles are outside, and each of them is 5 centimeter each. So figures are not drawn to a scale. So let us try to understand a concept by which we can solve this problem. That is, first you shall try to understand the number of equilateral triangles of each side 1 centimeter like this, that can be drawn in another equilateral triangle of side 5 centimeter each. So let us try to find out how many equilateral triangles of 1 centimeter each can be accommodated in this. Okay, so for this we need to consider equilateral triangles like this with 1 centimeter, 2, 3 and 4 centimeter like this, and in this first one we have one equilateral triangle. How many equilateral triangles are there inside this of 1 centimeter each? For this we have to choose the midpoints of all the 3 sides, join them in an order like this. So we got equilateral triangles of 1 centimeter each. So if you just count, you will see that there are 4 equilateral triangles are there. In this figure, if you want to find out the number of equilateral triangles, divide each side into 3 equal parts, join them in an order like this. Okay, and now you got equilateral triangles. Count, you will see that there are exactly 9 equilateral triangles are there. Okay, in this you make it into 4 equal parts and like this, and join them in an order. Okay, now you will see that equilateral triangles are formed of exactly 1 centimeter each. If we count, 16 equilateral triangles are there. 16 equilateral triangles are there. Okay, so there seems to be a pattern here. Let us try to understand this by then drawing a tabular column, and let us enter or make all our observation so that we can take some decisions. So in the first row, let us try to enter the length of each side of an equilateral triangle. In the second column, number of equilateral triangles of 1 unit each. So if each side is 1 unit like this, then we will have only 1. If each side is 2, there are 4 equilateral triangles. If each side is 3, then we have 9 equilateral triangles. If each side is 4 centimeter, we will have 16. If each side is n unit, children, for this 1 can be written as 1 square, 4 is 2 square, 9 is 3 square, 16 is 4 square. So definitely you have to just square this. Square of n is nothing but n square. So n square number of equilateral triangles can be formed. the number of equilateral triangles of 1 unit each in another equilateral triangle of each side n unit each is nothing but, don't you think it is n square, children? So we got this result now. With this, now let us count the number of equilateral triangles in each row, children. So it is 1 plus 3 plus 5 plus 7, which is 16. Incidentally, you also know that the sum of the odd natural number, the first n add natural numbers, is also given by the formula n square only. So here is an equilateral triangle of 5 centimeter. Let us make it into 1, 2, 3, 4, 5 equal parts. This side also 5 equal parts. So now let us try to fill up each row by an equilateral triangle of 1 centimeter each. So in the bottom row we have got 9 equilateral triangles. In the next row we have got 7. In the third row we have got 5. In the fourth row we have got 3. And finally we have got 1 equilateral triangle. So we have 25 equilateral triangles of each side 1 centimeters are there. In another equilateral triangle of each side 5 centimeter. Okay, with this information, I think we can attend to the problem. Here is a regular hexagon. So you just draw all the diagonals, and we know the diagonals bisect each other. Therefore, each segment has to be 5 centimeter and each interior angle is 60 degree. 6 equilateral triangles are there. So in one equilateral triangle we can draw 5 square equilateral triangles. Therefore, the number of equilateral triangles is 5 square into 6. 25 into 6, that is 150 equilateral triangles can be drawn in this. So in the next slide you will see all the 150 equilateral triangles in just 2 colors. This is the first one, second one, okay, the third, the fourth, fifth and sixth. So beautiful, you know. So these are the 150 equilateral triangles. Now let us go to the star figure. So inside this we have got a regular hexagon wherein each side is 5 centimeter. Therefore inside we have got 150 5 square into 6, that is 150 equilateral triangles, and outside we have got 6 equilateral triangles plus another 150. So therefore we have got 300 equilateral triangles, which you are now going to see in this figure. So you are seeing the equilateral triangles outside the figure, outside the regular hexagon. Now you see inside now in 2 different colors. Okay, these are the equilateral triangles inside. So altogether this comes to 300 equilateral triangles can be drawn inside this star. So we conclude that in number of equilateral triangles in a star is definitely greater than number of equilateral triangles in the hexagon. So here is a summary of all the 8 theorems that we have learned in these 4 sessions, the general enunciations only. So this is axiom 5.1 SAS, theorem 5.1 ASA, this is 5.2, 5.3 on isosceles triangle, this is theorem 5.4 SSS, this is theorem 5.5 RHS. Okay, you also prepare a chart like this. Now in the next slide you are able to see 5.6, 5.7, 5.8 on inequalities in a triangle. So children, in this 4th and the last session on triangles, we have discussed 2 alternate proof for theorem 5.2 and 5.3 with 3 more theorems on isosceles triangles, also theorem 5.6, 5.7, 5.8 on inequalities in a triangle, along with the worked examples with exercise 5.4 and 5.5 problems. So this is the homework, children. 7 problems are there. Please try to attend to these problems. So hope you have enjoyed the chapter triangles. Children, there is a saying, practice will make perfect. It is not that perfect practice will only make us perfect. Perfect practice means practice with thorough understanding of the concept will only make us perfect. So ಓದಿನಲ್ಲಿ ಪ್ರಾಮಾಣಿಕತೆ ಇರಲಿ ಅಂತ ನಾನು ಅತ್ಯಂತ ಕಳಕಳಿಯಾಗಿ ನಿಮ್ಮನ್ನು ಕೇಳ್ಕೊಳ್ತಾ ಇದ್ದೀನಿ ಮಕ್ಕಳೇ. ಓಕೆ, ಸೊ ಇಫ್ ಯು ಆಸ್ಕ್ ಮಿ ಎ ಕ್ವಶನ್, ವಾಟ್ ಈಸ್ ರೀಡಿಂಗ್? Reading is this, reading is nothing but raising the questions and removing the doubts then and there only. Okay, so you better write a diary like this. So for all the 7 days before you go to bed, these are the columns: date, time, subject, concepts understood, and then signature. Total number of hours you studied. This better you write, you maintain a diary like this. Be regular, sincere to your studies. Work out as many good number of problems on the each and every test from other resources. Take care of your health. Thanks for watching. Namaste children. Namaste.